Today's lecture is basically showing how we can extend control techniques for the rigid robot to the flexible joint robot. So if you've tried out any controls on the rigid robot so far and got some stuff working, after this class you'll be able to try it out on a flexible joint robot. So before we go to the whole complicated model of a robot, let's just deal with the simpler case of two masses attached by a spring. Displacement d1 for m1 and displacement d2 for m2. And I better put in some nonlinear friction in here, because if I don't have anything that's nonlinear, then you might as well use a linear control. So we'll have to justify what we're doing with some nonlinear friction. So the spring force is K times d1 minus d2. So if that's in SI units, that'll just be in newtons. If the masses are in kilograms, the control would be in newtons. d1 and d2 would be in meters. So there's two kind of cases here. Depends kind of what you're interested in controlling. So control systems usually say the output is y. You make y equal to one of the states, meaning that's what you want to control. So if you want to control D2, use backstepping or feedback linearization. So I underline backstepping because that's what I'm going to show you how to do today for case 1. I'm not going to show you the feedback linearization for case 1. Backstepping for case 1 is much easier because we can make it adaptive. We can throw in neural networks. Trying to make feedback linearization adaptive is very, very difficult. So I'm not going to try and do it. Because, but on the other hand, if we have case 2, we have y equals d1, that's when we want to use feedback linearization. So feedback linearization can work for both cases, but case 1 is much easier with backstepping. So I will get into feedback linearization a bit to show you how to do case 2 if we want to control d1 and we don't really care what d2 is doing. Of course, when we get to the flexible joint robot, then this will be the analogy of, like, this will be the link angles, this will be like the rotor angles. So obviously the flexible joint robot case, we're going to be doing the backstepping because we're going to be interested in controlling the link angles accurately in the robot so that the end effector of the robot is in the right position. But let's go through these two and show you how to do it. So the equations of motion, all I have to do is good old force equals mass times acceleration to derive my equations of motion. So if I just say the sum of forces is equal to the mass times the acceleration for each of these two systems. And for system 1, I get u minus k d1 minus d2 minus b d dot equals m 1 d1 double dot. So I have control force coming in, I have spring force, I have nonlinear friction force equals mass times acceleration. So just add up all my forces, that's mass times acceleration. The spring force in the other one is kind kind of equal and opposite is the idea here. Okay, so we just kind of get a simplistic form of the kind of equations we got when we did the flexible gyro robot. So it's a lot like the flexible gyro robot, just a lot simpler. So much easier to teach the technique with this. So let's do backstepping first. We're doing case 1 here, where we want to control the position D2. So I'll make x1 equal D2, x2 equal D2 dot, x3 equal D1, x4 equal D1 dot. And my equations of motion are x1 dot equals x2, and x2 dot equals k over m2, x3 minus x1 minus b over m2. This is b of x2 over m2. And I get, so everyone have these? And I get x3 dot equals x4, x4 dot equals negative k over m1, x3 minus x1 minus b of x4 over m1 plus u over m1. So those are my equations of motion written in terms of my states. So I'm going to define my auxiliary error to z1 equals lambda x1 plus x2. So backstepping goes in steps, and the way it's going to work is the idea here that I could design, if I could pick what x3 was, then I could design a stable control for this system. So if I had like perfect power over x3. So first of all, I'm going to design a desired value of x3 that would be a good controller for this system. And then I'll go to the next equation, and I'll design a desired value of x4, such that if x4 reaches the desired value, it would make x3 go to its desired value. And then I'm going to backstep one more step, and I'm going to design the actual control input that will actually force x4 to go to its desired value, which will in turn force x3 to go to its desired value. So that's one way to think of it. Another way to think of it is just that think of this as the torque. And so like in a physical way, by deciding what x3 is, I'm actually deciding how much that spring is twisted. So I'm actually designing a control torque for this first link, for this first mass, I should say, using the spring torque. So x3 determines the spring torque. And so, but then I have to design the actual velocity of that, so the derivative of that spring torque as well, not just the spring torque. Going to come in steps here. So you get V1 is M2 over 2K times Z1 squared. V1 dot is going to be Z1 M2 over K lambda X2 plus X3 minus X1 minus bx2 over k. So you can see why I stuck this m2 over k in here. It's because it made sure that this term here was kind of by itself. So now I have like an x3 that I can design to control this system. And I don't have anything multiplying the x3, which makes it way easier. Because otherwise I'd have to like divide by whatever's multiplying x3, which is kind of a pain, especially when you go and make things adaptive. So the real advantage to this, adding m2 and k right in the Lyapunov function, we'll see when we make things adaptive. And then we don't have to have some adaptive parameter that's getting inverted in front of the x3. It just makes things way, way easier. So now we'll define alpha 1 as the desired value of x3. We will call this the virtual control. Because it's kind of like a control. It looks like a control when we do the math, but we don't actually have perfect control of this, so we can just decide exactly what we want it to be. It's more like a desired value. So the error in the second step of backstepping will be Z2 equals x3 minus alpha 1. So in the second step, we try to make Z2 go to 0. In other words, x3 go to alpha 1. Okay? So we'll rewrite v1 dot here as z1 m2 lambda x2 over k minus b x of x2 over k minus x1 plus z2 plus alpha 1. So this here is my x3. So I've kind of substituted something for x3, so I don't actually have x3 in there. So I can't do anything about z2, but alpha 1 can take care of everything else in that equation. So I would have all this stuff. So choose alpha 1 is equal to x1 plus b x2 over k minus m2 lambda x2 over k. So I want to cancel out all those terms in there. So I basically want all these terms that I don't like to disappear. So I'm just going to cancel them out. And then you can see, like, I want v1 dot to be negative definite, right? So what am I going to multiply by to make sure this is negative definite? Just like a minus kz1. So that, then I'll get like a v1 dot equals minus k z1 squared. Okay? So I have all these basically canceling terms that are trying to cancel everything out, and a feedback, linear feedback term. Yeah?
Like k is like the coefficient.
Or, sorry, yeah, let's use, I didn't mean to write k. Exactly right. I should write, I'm gonna use, what should I use? Oh yeah, G. Okay, I'll just call it K1. Maybe a small K1 here. It's gonna look really different. There we go. Totally different than my spring constant, right? Okay, thank you for that. So that's just feedback control, not the spring constant. So then, V1 dot is equal to minus K1 Z1 squared plus Z1 Z2. So we can see it didn't work perfectly, but we don't expect it to. We still have this Z1 Z2 in here that's making it not negative definite, but of course, because we're only designing a desired value for x3, not the actual value of x3. So step 2, we'll do V2 is equal to V1 plus 1/2 Z2 squared. V2 dot is equal to V1 dot plus Z2 x3 dot minus alpha 1 dot. V2 dot is equal to minus K1 Z1 squared plus Z1 Z2 plus Z2 x4 minus alpha 1 dot. Our alpha 1 dot will have to be calculated analytically. So this is where your MATLAB symbolic math comes in handy. I mean, obviously this example is pretty straightforward, but you can imagine in general in control systems, if you're trying to take an analytic derivative, it's going to get really messy. So this is the kind of formula you're going to type into MATLAB symbolic math to have it spit out these analytic derivatives for you. Which can result in really complex controllers with pretty complex equations. But by the end of the class, we'll see how we can also just replace those things by neural networks as well, which actually makes things simpler than trying to take the analytic derivative sometimes. Sometimes a neural network is actually way simpler than one of these derivatives, because these derivatives can be enormous. So let alpha 2 be the desired value of x4, second virtual control. The error for the third step of backstepping is Z3 equals x4 minus x2. So obviously we want Z3 to go to 0. V2 dot is minus K1 Z1 squared plus Z1 Z2 plus Z2 Z3 plus alpha 2 minus alpha 1 dot. So I just replaced x4 when I did that substitution. So we got this. So choose my virtual control alpha 2 to be minus K2 Z2, and then so I want to create a feedback gain. I also want to cancel out this term here, alpha 1 dot, which I know because I calculated it analytically. But I also need to make sure this term disappears here as well. So to make sure this term disappears, I'm going to do minus z1, okay? So minus z1 will cancel out that z1, z2. And then I have plus alpha 1 dot. So this, alpha 1 dot is not, I'm not differentiating anything here with a differentiator. I'm analytically differentiating. So this is an algebraic expression. It's not some output of a differentiator, okay? Don't ever put a differentiator into MATLAB simulating unless you really know what you're doing. Bad idea. Okay. So that's an analytic derivative. Important to point out. Then v2 dot is equal to minus k1 z1 squared minus k2 z2 squared plus z2 z3. And now it's kind of boring because we just do exactly the same thing. So v3 will be v2 plus m1 over 2 z3 squared. And I'm just going to do the exact same thing in this step of backstepping that I did in my previous step of backstepping. So v3 dot is equal to v2 dot plus m1 z3 x4 dot minus alpha 2 dot. Alpha 2 dot must be calculated analytically using my MATLAB symbolic math probably in general. v3 dot is minus k1 z1 squared minus k2 z2 squared plus z2 z3 plus z3 minus k1 x3 minus x1 minus b of x4 plus u minus m1 alpha 2 dot. So now I can choose my actual control u to be m1 alpha 2 dot plus k x3 minus x1 plus b x4 minus z2 minus k3 z3. Then b dot is equal to minus k1 z1 squared minus k2 z2 squared minus k3 z3 squared. This is a negative definite Lyapunov derivative. So backstepping is very popular, but people do complain about the complexity. I did a backstepping design once where alpha 2 dot ended up being a 10 kilobyte ASCII file. So it can get big. So people do complain about the complexity of it. But like I said, we don't have to worry about it too much because we'll be able to see how to approximate this term with a CMAC neural network easily enough. And so that it basically becomes rather simple to design the control. So I should point out what kind of systems this is used for. So you can use backstepping as long as your system is in strict feedback form. So any form that's in the form of x1 dot equals f1 of x1 plus g1 of x1 x2, x2 dot equals f2 of x1 and x2 plus g2 of x1, x2, x3, all the way down to xn minus 1 dot equals f n minus 1, x1 all the way to xn minus 1 plus g n minus 1, x1 all the way up to x n minus 1 of x times xn, xn dot equals f of x plus g of x u. So not all nonlinear systems are in that form, but there's an awful lot of real life examples that are either in this form or close enough to being in this form that it'll work really well. So you can see at each step here, x2 only appears here, so I can design a desired value for it really easily. x3 only appears here, so I can design a desired value for it really easily. And there's no higher x's in there that I can't account for, because it has to be kind of sequential. Does anyone have any questions? So we'll see how to make this adaptive. You can also make it robust. So it's very handy for nonlinear controls. So basically, if systems are in a strict feedback form, nonlinear controls are pretty straightforward. If systems are not in this form, then nonlinear controls become really hard. And I'm not teaching about those kind of nonlinear controls in this course. I'm kind of assuming that anything you encounter will be in backsteppable form. Any questions on backstepping? Okay, so I'm going to take a bit of a sidetrack here, because I'm going to show you how to treat case 2 in that situation with my two masses in the spring. And it's not directly related to the flexible joint robot, because that would mean in the flexible joint robot, that would mean you're only trying to control the rotor angles. You need to care what the link angles are doing, which is probably not the way you want to control a robot. So it's not so practical for the robot. But if you're dealing with any other kind of nonlinear system, then you will want to know about feedback linearization. It will be handy. So I should teach it to you as part of the nonlinear control course. So case 2 was where y equals d1 is the output. Use feedback linearization. So the rule in feedback linearization is to differentiate until the control appears. That's exactly how you do it if you wanted to use it for case 1 as well. So we have y equals d1, so we're just going to differentiate until we see a u. In this case, we don't have to go very far. Once we get to y double dot, we have 1 over m minus k d1 minus d2 minus b d1 dot plus u. So once you've got a u in your equation, then you can design u. So design my u like that, then I get something that's stable, minus k1y minus k2y dot. Should be a plus, I guess. There. So again, I was just canceling out my nonlinear terms, and then I wanted to make a nice little linear feedback term, a general control strategy. So what I get here is a stable linear system. In other words, y goes to 0 as t goes to infinity. If the zero dynamics are stable, so I mean, if this, it looks good for d1 here, because d1 is equal to y. So we knew d1 is going to do what we want it to do. But if d2 goes off to infinity, it's no good. The system's still unstable. So if the zero dynamics are unstable, are stable, sorry, the zero dynamics so you kind of have this extra task where you have to analyze the zero dynamics to ensure that they're stable. So the zero dynamics is the equation that we didn't deal with because we are obviously dealing with this equation in the system, but we're not dealing with the other equation. So this is one for mass 1, but what is mass 2 doing? We got to make sure mass 2 doesn't go to infinity. That could be bad. So for the other mass 2, we have k d1 minus d2 minus b d2 dot equals m2 d2 double dot. So we'll define z1 to be d2 and z2 to be d2 dot.